Pen tracing puzzle. Pen tracing puzzle is a computer version of the classic pencil and paper puzzle, which can object is to trace the diagram without taking the pencil off the paper and without going over the sum line twice. Pen tracing puzzle is a computer version of the classic pencil and a paper puzzle in which the object is to twice trace. You may have puzzle like this one. Can you draw the diagram at the left without lifting your pencil from the paper and without tracing over the sum segment twice? By trial and error. You may notice that only certain starting points seem to allow a complete tracing. Pen tracing puzzle can be considered a problem in graph theory. If we image a vertex place whatever two lines meet or cross over each other, then we have a graph without repairing an edges.
We learned in this section a graph has an angular path only if two vertices are of odd degree and the remaining vertices are of even degree. Furthermore, the path must start at one of the vertices of odd degree and end at the other. In the puzzle, in the upper figure at the left, only two vertices are of odd degree, the two bottom corners. The lower figure at the left shows one possible solution. Of course, if every vertex is of even degree, we can solve the puzzle by finding an Euler circuit if more than two vertices are of odd degree. Then we know the puzzle cannot be solved.
If you can find a way to trace the shape without lifting your pen and without tracing over the sum segment twice, only take 10 steps in an interaction at the middle. Label the top vertex of the triangle at the top 1. The top left vertex of the square 2, the top right of the square 3, the bottom left of the square 4, the bottom right of the square 5, and the bottom vertex of the triangle on the bottom 6. The path is 3, 1, 2, 3, 4, 6, 5, and 2, 4, 5, 3.
Now we are looking for a path or a cycle in the graph that visits every edge exactly once. This problem was solved by the famous mathematician Euler in the 1936 and is considered to be the beginning of the graph theory. The problem is often referred as an Euler path or Euler circuit problem. An Euler path starts and ends at the different vertices, whereas in Euler circuit
we'll talk about graph coloring. If the map is divided into regions in some manner, what is the minimum number of colors required if the neighboring regions are to be colored differently? This question originated not with map makers but with mathematicians. In the mid-1800s or in 1852, Francis Guthrie was trying to color a map of the countries of England so that it would be easy to distinguish the countries. He wanted countries sharing a common border to have different colors. After several attempts, he noticed that 4 colors were required to color the map, but not more. This observation became known as the 4-color problem. It was not proved until over 100 years later. We have this contiguous map here of United States. This map has only 4 colors, and that no states share a common border have the same color. There is a connection between map coloring and graph theory. Maps can be modeled by graphs using the countries as the vertices, and two vertices or the countries are adjacent if they share a common boundary, representing maps as graphs. We have this fictional map on the right. It shows the countries labeled as letters, of a continent. We can represent each country by a vertex placed anywhere within the boundary of that country. We will then connect two vertices with an edge if the two corresponding are neighbors. The countries that touch at just corner point will not be considered neighbors. As you can see here, the D and the B, we won't be considered neighbors. If we erase the boundaries of the countries, we are left with this graph. The resulting graph will always be a planar graph because the edges simply connect the neighboring countries. As you can see, the graph is tricolorable: yellow, blue, and red. Note that no two vertices have the same color. This colored map here is based on the colors of the vertices of the graph. Representing maps as graphs, we drew a vertex in each region, the country, state, etc. of the map. We connect two vertices if the corresponding regions share a common border. The four-color theorem states that every planar graph is four-colorable. In some cases, less than 4 colors may be required. Also, if the graph is not planar, more than 4 colors may be necessary. This theorem was finally proven in 1976 by Wolfgang Haken and Kenneth Appel. To mathematics.
Hi everyone, my name is Robert Pirampuyo. In this lesson, we all tackle about application of graph coding. Without further ado, let's get started. First of all, we have a coloring and chromatic number. A coloring for a graph is a coloring of the vertices a way that the vertices joined by an edge have a different colors. For example, in this graph, we see the endpoint of one edge, two vertices, one red and one blue. If you analyze any of edge of this graph, you see the two vertices are different color. The chromatic number of a graph is the least numbers of the colors needed to make a coloring. If possible, the coloring are we looking for is the least number of colors needed, and it's not possible if it's not. But if told this is a fact, the minimum coloring, then we can determine its chromatic number just counting the number of colors. For example, this diagram shows the minimum coloring of the Peterson graph. What is the chromatic number? If your answer is 3, you're correct. Because there are 3 colors required, blue, red, green. If we attempt to use 2 colors, then we find impossible to avoid having an edge with the 2 of the same color vertices. Coloring graph. I will show you the step-by-step of coloring graph. Step 1. Choose a vertex with the highest degree and color it. Use the same colors to color as many vertices as you can without coloring the vertices joined by an edge of the same color. Step 2. Choose a new color and repeat what you did in step 1 for vertices not already colored. Step 3. Repeat step 1 until all vertices are colored. For example, color the graph below and give its chromatic number. We're gonna start by choosing a vertex. Here's the degree. The degree is just a number of edge that just attach in vertex. The vertex as the highest degree is 5, so we can color this. You can choose any color of your want. Then, I'm going to find the vertices that are not joined to this particular vertex by a single edge. Then, I'm going to find other vertices that are not joined to this particular vertex by the single edge. I'm going to color them as green. For example, here. Then, all of the remaining vertices are degree 3. So any of one of them will work. I pick this one and color it with red. Then I'm gonna color other vertices green, as many as I can. But I need to avoid other vertices For example, here. Then we color this one. Avoid all other vertices that connect to this one. Then we color this one. Then lastly, repeat step 1 until all vertices are colored. So I'm gonna choose blue to color all vertices. Conclusion: if you experiment with a different coloring, you will find its chromatic number is 3 as it appears to be in the graph above. The coloring of graphs is used to solve a practical problems such as scheduling problems in science, allocations, transmissions, frequency to TV and radio station study of cell phone traffic. Coloring maps show the two regions that shares a boundary are the same color.
We tackle about the chromatic number of a graph. And now, what is the meaning of vertex? The meaning of vertex typically means a corner or a point where the lines met. In a plural, it is vertex. A coloring for a graph is coloring of the vertex in such a way that vertices joined by an edge have different colors. In a graph theory, the collection of dots and lines is called a graph. The dots are called vertices and the lines between them are called edges, coloring the vertices in the way that was illustrated. Note a vertice that share an edge have the same color. It is called a proper coloring of a graph. This scheduling example is a simple example that we can find the chromatic number of the graph. If we start by coloring vertex A with the color red, then we can see that vertex B and C must be of different color than this since they share an edge with A. Furthermore, B and C also share an edge, so they have to be different colors as well, say blue and green. The only vertex left is D, and we see that it shares an edge with both B and C. So it can be blue or green, but it does not share an edge with A, so it can be red.